Welcome to this video. It's discussing broadband matching networks designed the easy way. My name is Dean Monty, and I had worked at TriQuint Semiconductor for about 30 years as a packaging engineer, and I have a little bit of an unusual background for this topic in that I'm a ceramic engineer working in the packaging area. However, during the time that I worked at TriQuint, we were working on the early days of cell phone development and creating modules that had the matching networks built into the module. And so I worked directly with the design groups and developed a keen interest in matching networks in that they had a big impact on the yields of our parts. And so I wanted to really understand the details of how they work. And so a lot of what I'm going to go over is stuff that I don't think is published anywhere else that I have seen as far as the relationships within the matching network and how the components interact. And so to start with, I want to cover some key points. And the first point is that anytime you have a C that is equal to the inductor time divided by the input impedance times the output impedance, that will resonate at some particular frequency. So as long as that criteria is met, you'll get a resonance. And in this case, I've got a sample up here of just a single LC. And what happens is that if you then take that LC and you split it between the two and you shift the L over and the C out to the outside and drop in a copy of that and mirror image it, you end up with two resonances occurring. Initially, if the L values are the same in both cases, the two frequencies will be spread way apart. However, you can scale these L's and bring those closer together. So by splitting the circuit and then you end up with the L and C mirrored in the middle, you then get these two separate peaks. And then scaling the L's while keeping the C's in the correct ratio to those two L's, you'll get F1 and F2 frequencies resonating, and you can move those around by changing the L values. This technique is really easy using QucsStudio and SimSmith, which are the two graphics I showed on the beginning slide. And both of those tools are free and pretty simple to use. QucsStudio is kind of similar to ADS, and SimSmith is similar to the ADS tool for doing Smith chart matching, although it has quite a bit more capability, I think, than the ADS tool. And so it's really worth playing with that to get to know it. As far as complex input impedance, so everything that was discussed up here was all talking about a real impedance. If we talk about having a complex impedance, basically treat that after the fact, after you've already done some stuff for the real part of the impedance, then you end up doing some tweaks to handle the complex input impedance. And then also a big typical thing to worry about with amplifiers is if you're driving them into compression, they tend to want to worry about suppressing harmonics. And so we'll be discussing how you would handle that in the match as well. Now this methodology is also useful for filters as well, in that you can treat those just as a 50 ohm to 50 ohm match. And so it's going to block some frequencies and let others through. Okay, a lot of this was discovered because I happened to pick out a sample case to play with that was a 2 ohm to 50 ohm match. And it turns out that that has some really almost magical properties that you end up with a 2 times 50 for the input times the output impedance is 100. And then a property called geometric mean that we'll be using quite a bit is the square root of the Z in times Z out, which is 10 in this case. And normally you would start off to calculate an L and a C for just a simple LC match, a single LC match. You would do this kind of a calculation based on calculating a Q value and then extracting an L and a C from that Q. But that's kind of a cumbersome way in my thoughts as to how to calculate that. If we just look at some inductor at a given frequency, you can calculate that based on a triangle that is a triangle in the complex impedance plane, where you're looking at the geometric mean, so this 10 number that we've got up here minus the input impedance squared over 2 pi f to get your inductance. And so in this case, that turns out to be the square root of 10 squared minus 2 squared over 2 pi f. So again, this is just a right triangle calculation for the reactance of L. Now it turns out that from that you can just divide that by 100, and for the 2 to 50 ohm case you can divide that by 100, or the Z in times Z out, and get your capacitance value. It is possible to calculate the C of at a given frequency in a similar fashion to what we did the L, which is just the admittance plane instead of the impedance plane. And if we use these calculations at 10 gigahertz, we get 155.9 picohenries, and then dividing that by 100, we get 1.559 picofarads. And in any circuit, you can scale just by multiplying all the components in the circuit to a different frequency. So if we do that for 15.59 gigahertz, we end up getting 100 picohenry and 1 picofarad. So you can easily see the relationship as 100 to 1 in this case. Now, if you happen to be working in higher impedance circuits like antenna matching, a similar example that will give you some insight is a 50 ohm to 200 ohm. Since the C in that case is L divided by 10,000 and the geometric mean is 100, you'll have similar kind of nice, easy to see relationships on these. So the first tool we're going to talk about is SimSmith, and this was written by a guy named Ward Hartman. That's in the amateur radio field and had written the software for his own use. And so it's freely available. You can download it and play with it, and it's got a lot of capabilities in it. It's not just a matching network tool. It does a lot of fair amount of circuit simulation, and it also ties into a vector network analyzer, an inexpensive one that's used for ham radio. And so here we can see a sample where we're matching again a simple single LC from 2 ohm to 50 ohm, and that has this follows the path on the Smith chart for that component and so this chart is for a single frequency. You're looking at the translation of the inductor to get up to 10 ohms, and then the capacitor to get down to 50 ohms. So those are crossing over this 10 ohm curve that's shown here. Now if we normalize, instead of the 50 ohms in the middle of the chart, we normalize to 10 ohms, things become a lot more obvious. That you end up having the inductor is going from 2 ohms up to 10 ohms, and this dash line is showing the 10 ohm line that we had. It's a bent over version of the triangle that we calculated earlier. So we've got 2 on this leg, 10 on this leg, and that results in a reactance of the inductor along this line. So, and the capacitor is a mirror image of that on the right hand half of the Smith chart. And that's for a single LC. Then this drawing down here is showing a LCLC match, so a two resonator match, and we'll be going into more detail on that. So this graph is showing the symmetry of the LCLC match, so the bottom plot that we showed in the last chart. And it turns out that all these numbers down here are the geometric mean of every combination of the impedances. So the 10 ohm is the geometric mean of 2 and 50, and then the 2 ohm and 10 ohm, the geometric mean of that is 4.47, and from 10 ohm to 50 ohm the geometric mean is 22.3. So these give us these Z values at all these different points. And all these equations down here are fairly simple, but we really don't need those because later we're going to get into just how to do all this graphically on the SimSmith and on the QucsStudio programs. But I will provide also spreadsheets that include all of this information in it, so you can just type in the numbers, both input and output impedance, and it'll calculate all these for you. Okay. So the other question was, how do you handle the complex Zn? And so it turns out that this first inductor, if you're at somewhere up off of the real impedance line, you're either below it in the capacitive area or above that real impedance line in the upper part of the Smith chart, that you can either adjust the length of this L to compensate for that. So it can either be bigger or smaller L depending on whether you're below the real line or above the real line. And if you get too high up here, you end up compensating by deleting the inductor and going with a series cap as your first element, and then doing the translations over to get to 50 ohms. And so these calculations down here just take care of that, where if the L turns out to be a negative number, you then use the capacitor, because it's basically indicating that it's past that point on the Smith chart. Now there is some additional relationships which are just interesting. It turns out that if you look at these impedances for these different combinations, they all end up as a multiple of 5. And so we can either divide capacitors by 100 to get the capacitors, or you can divide one capacitor by the other, divided by 5 will give you the same result. So we either get 4 picofarad from this calculation or 4 picofarad from that calculation. And similarly with the L's are in a ratio of 5 to 1 for the L2 over L1, and the C's are in a ratio of 5 to 1 again down here. Okay, and that was all of the previous couple of slides were for a 2 resonator match. This is now extending that to 3 resonators. And so we get the similar kind of calculations, and again, this will all be in an Excel spreadsheet that you can link, that's linked to in the description. And same kind of thing is that for the initial first inductor, you may have to replace that with a capacitor or adjust the size of the inductor based on these equations down here. And again, that'll be in this spreadsheet. I just included the Q's on here just for interest's sake. We don't ever have to calculate these. Okay, to summarize the complex impedances, I also included a graphic representation of that down here, where because I got so high into this part, into the upper part of the Smith chart, use a capacitor to get back down to the point where we can do the translations to get over to 50 ohms and with 3 resonators. And so and this is just the same thing I've been describing, is that the complex impedances are handled by adjusting that size of the first inductor. Make it smaller if you're up in the upper part of the Smith chart, make it larger if you're in the lower part of the Smith chart. And then for a really large imaginary Zn, then you end up using this series cap as a beginning component. Okay, now the next topic I'm going to cover here is the harmonic suppression. So harmonic suppression is useful for where you're going to add an inductor into the leg of each capacitor, or one or more capacitors, so that you can create a harmonic suppression element. And equations that I've got down here allow you to adjust the position of this harmonic suppression trough anywhere in the frequency that you want without affecting the match at the target frequency. You can adjust the N value within these equations with as a tuning element in the circuit simulation, and just slide that harmonic suppression anywhere you want within this range, anything higher than what the fundamental frequency is. So by adjusting the N value, you can either target the second harmonic, third harmonic, or fourth harmonic, or any other frequency that you want. Okay, so this is showing a simple LC match in QucsStudio, which is written by Michael Margraf. And this is also another free tool, and it's a circuit simulator, somewhat like ADS. And so in here you can, as long as you keep the C value equal to the L divided by the Zn times the Z out, you can then slide that to that frequency to any point that you want for the resonance. And if you notice down here, you get a large loop in this case. Okay, now if we split that circuit, so we separate the first inductor and the first capacitor and drop in a second inductor and cap, then these are mirror imaged from the first two, and those result in a second resonance at a higher frequency. And when you introduce that into the circuit, you drive the original frequency down, and then you add this second resonance at a higher frequency. And if you notice, these create these big loops down here in the bottom of the Smith chart. And then what we're going to do is put in tuning parameters. So this is a tuning block in this tool. And create, in this case I've created a P1M for a pair 1 multiplier, so that's multiplying this L and this C together and keeping them in the correct ratio. And then the P2M is for this L2 and C2, and scales both of those to move that higher frequency trough around. So now, just by moving these up and down, you can move these along and squeeze those two resonances together. So this is more versatile than what I showed earlier on those hand calculations for creating an LCLC match. This one you can adjust any frequency. You can squeeze these together to get better performance right at the fundamental, or you can spread them apart if you want broader band, but you're willing to accept some poorer performance right in the middle of the band. And notice that from the last plot we had huge circles down here. This has now collapsed those circles down into, or that circle down into a small loop. It passes through the 50 ohm point twice, and so that's where these two resonances are occurring. Now, one just comment here is that in the SimSmith tool, when you plot this type of a LCLC match, what you'll see is that you get a symmetric circuit at the one frequency, at the two frequencies where it's resonating. You'll get symmetric performance on this kind of a plot. So this one is symmetric at the higher frequency, symmetric at the lower frequency, but any other frequency either between those two or above or below those two is asymmetric. And the plots that these are showing the translation of the component at a single frequency. Now, if we want to make this generic, we can then add in tuning variables for the input impedance and the output impedance, and then the C's now become a function of the Zin times Z out. And I also have made, in this case, the L2 is a ratio to L1. So if I scale L1, I move everything because all the other components are going to track with it. That'll just move everything in frequency, so it becomes a scaling parameter for the whole response moving up and down in frequency. And then Z in and Z out are tunable. And in here I've added the output values for these components in, so as you do the tuning with those sliders that I showed on one of the previous slides, as you tune it in, you'll end up seeing these component values change. Now you can also do some odd things where you can, if you had a reason to, I'm not sure what advantages this would have, but you can add in slight offsets to the capacitor values to then create a loop around the 50 ohm point. So that flattens off and gets rid of your two resonant troughs up here. And it may have some helpful functions for phase control. So that provides a more flattened off response. Now, if we go to the 3 resonance case, we get an even broader band with the 3 LCs. And so again, we've taken and split the middle components apart and dropped in another LC in here. So this center LC now is back to the original orientation that the first LC was. And again, you can tune these down. What you notice is that you get 2 loops down here now, so it passes through the 50 ohm point 3 times and creating these loops down here. And again, you can put in these offsets of the capacitor, and actually this has an additional offset. In this case, I fixed the 2 ohm and 50 ohm impedance, but made it, the impedance is variable within this tuning equation section. And that allows me to move this loop and create the loop by adjusting the capacitors, and then the circle can be moved left to right to center it over top of the 50 ohm point by varying the impedance, input and output impedance that are used to calculate the C values. And that flattens off this response down here, which again might be useful for phase control. Now this plot is showing that we've now added these inductors into the shunt capacitor legs and created 3 of these harmonic suppression resonators. So those 3 can now be aligned up to exactly to the harmonics of the fundamental, or you can, in the case of the next slide, you can push them together or position them at any one of, if you want to try and get a broadband harmonic suppression, you can squeeze those together at a particular harmonic. And so that may be useful for some types of amplifiers. Now, another odd thing you can do is, instead of going from 2 ohms to 50 ohms, you can go backwards to 0.6 ohms in this case. And so that's jumping in the reverse direction and then working your way over to 50 ohms. And what that does is ends up resulting in a smaller, the largest inductor that's in the matching network can be made to be almost half the size. So that may be an advantage for some cases. Now you lose some in the bandwidth, and it may have impact on losses. So I haven't studied that thoroughly, but it may be useful in some cases. Now the other thing that is nice about especially this graphical tool of SimSmith, it allows you to plug in Q values for the components, and then you're visually adjusting by just dragging these components around. You can adjust to compensate for any losses that you got for poor Q inductors. So of course you're still going to get some losses from the inductors, but it just allows you to adjust those to compensate so the match is as good as it can be. And that's much easier than a lot of the analytical approaches where you're trying to do calculations that depend on the components being perfect. This ends up easily allowing for the inductor Qs. Okay, one other unusual thing you can do with this technique is, because these resonators are all adjustable to any particular frequency, there is some interaction, but you can easily tune things just with sliders. And so you can create something that would be a dual band and broadband match, where you've got 4 LC components and you're adjusting 2 of them to be at one frequency and 2 of them to be at another frequency. In reality, the inductance of the ZN is probably going to change too, so to compensate for that, it probably would duplicate this and make a second one that has the other input impedance at the higher frequency, and then adjust both of those until you get them optimized. Now, I mentioned earlier that you can also use this concepts for filters, and I won't go into a lot of detail in this video. I'll probably be doing a second video on filters. But basically what you can see here is, if I for a 50 ohm to 50 ohm, the C's are equal to L divided by 2500. So 50 times 50 is 2500. So now you get this ratio where you can do this kind of a symmetric circuit for a matching network, and it has a low band or a low pass response type of response shown up here. And this is just a blow up showing more detail of this, where you can see how symmetric it is around that point. So the important takeaways are that C near the Z out and L near the Z in create a resonance whenever the C is equal to L over Z in times Z out. So that's kind of the starting point for a single LC match. Then we can add additional LC pairs in the middle, and mirroring it each time that you add another LC pair. That creates additional resonances. And that methodology also works for filters as well. And it even works for bandpass filters in a different variation that I talk about in another video. So every time you add one of these LC pairs, it's C is equal to L over Z in times Z out. So that's true through this whole assembly of these LC pairs. For complex parts of the ZN, the first L is either modified in size or replaced with a series cap, depending on what the input impedance is. Now this methodology is much simpler math than what I've seen elsewhere for broadband matches that use analytical approaches. The only thing you're really calculating is a geometric means at a bunch of different points, which is very simple. So there's no S-plane calculations like there are for filters, and no Qs are required, even though I showed a couple. Now this methodology also has much more insight into the component effects. So if you see a particular resonance that's messed up somehow, you can immediately identify which LC pair is causing that issue. And this method also easily handles lossy components graphically. And so especially on the SimSmith matching tool. You can easily put in very lossy components and just visually see the effect and how to compensate for it. So a very useful tool. So this concludes the general overview of broadband matching networks and how to create them the easy way. I have additional videos that are being posted on using QucsStudio and using SimSmith, and detailed training on those. So if you'd like to see those, please check them out. And I also have one on filters and how to apply the similar concepts to filters. So that's also available. So I hope you enjoyed this and get some use out of it.